Okay. So on Friday, we started talking about hypothesis testing. So before we were doing inference about a population, mean, or proportion by confidence intervals, giving likely values. And now we're at testing whether certain values are plausible. Right? We did kind of randomization last time. If we generated samples under the null hypothesis, would our actual sample look unusual enough? If it's consistent with what we would typically get, we don't reject it. If it's extreme relative to what the variation we're likely to get for X bar, then we end up rejecting it, including that the null hypothesis probably is wrong, there's some difference, some change. Right? And so today we're going to do the same type of thing, but with the formulas. So the scenario is that we have a population, and it has a mean. And we're going to have a hypothesis about that the mean equals some value. Null hypothesis. There's an alternative, which could be two-sided, could be one-sided, but basically says that it's not that value. Right? So the first one is the null hypothesis, and the second one is an alternative value that's just simply not that, or it's maybe different, less than or equal to. And then we're going to get a sample of data from that population, x1, x2, up to xn, and get a value of x bar. And then we're going to use x bar to assess these hypotheses. And so we're going to reject the null hypothesis in favor of the alternative if x bar is far enough away. Right? The basic idea is we reject the null hypothesis, reject it at 0. If x bar is far enough away from the null. And there's a medical study that were reported in the news over the weekend that did exactly this. Right? There's instead of taking pills to control HIV virus in people who are infected every day, right? They've been testing monthly shots. Right? And the basic question was, if you got a monthly shot, instead of taking the pills every day, and some people forget to take the pills, or right? It's a lot to take a regimen of pills every single day. They asked, it was about rates of infection rather than kind of an average like this. But a rate of infection is kind of but would the rate of infection be the same in those getting the shots as in taking the pills? And in this case, the rates were basically identical, that there was almost no difference. So they concluded that actually the shot could provide equal protection to taking the pills every single day. Plus, when they asked people if they liked that, I said, yeah, that's a lot better, because then I'm not trying to remember to take pills multiple times per day and keeping track of these things and so on. And it was just much easier to get the monthly appointment, to get the shot at a doctor or nurse. But if that proportion had been much less, much different, they probably would have rejected the hypothesis and said, no, it's not as good. And that's the essential case that we're up to here. What we're dealing in terms of X bar, right? So how far away does it have to be? Right, so if you draw any picture here, here's the mu sub 0 under our null hypothesis, right, null value. And we're going to get a value of x bar. So this is our value of x bar. This is the timeline line for x bar, right? The number line. And so is x bar far away? How do we tell if it's sufficiently far away? Well, sometimes you just on an absolute scale when you're thinking about something. Is it 1 unit away, 2 units away, 3 units away? It might make sense to you that something is far away. But if we have a small sample, kind of unusual things can happen pretty regularly. Right? You get one or two small values out of a small sample, or large values, and things can swing pretty far. So we look at the sampling distribution of the bar. We compare this distance to what we would expect under the sampling distribution of x bar. Under the null hypothesis. Assuming the null hypothesis is true. And so if under the null hypothesis and that sampling distribution, what we've seen is an unusual event. If it's way out there in the tails, if it's something that's going to happen less than 5% and be an unusual thing away from u sub 0, we're going to judge that as sufficient evidence that it's likely not right. Right? The u sub 0 is likely not right. So under the null hypothesis, it says u equals u sub 0, and really the central limit theorem, right? That says x bar is approximately normal. X bar's distribution should be approximately normally like a bell-shaped curve, centered at u sub 0, right? At the null mean, if that's true. And then the standard error is sigma over the square root of n. And it gets, the sampling distribution gets narrower and narrower as you get big sample sizes. And we understand what's unusual under normal. Right? At 5% level, about 95% of the values are plus or minus about 1.96. So looking at a standard normal, z value is 0. The two values that cut off about 95% of the area, 1.96 and negative 1.96. At least about 2.5% in this tail, and about 2.5% in this tail. This is actually, this 1.96 is actually the 97.5th percentile of a normal. It's the 95% plus this extra 2.5%, so 97.5. And so anything that's out further here or out further here is away from the middle of 0 and is kind of unusual, right? It doesn't happen that often. So we're going to translate that into, we're going to reject the null hypothesis at what we call an alpha, 0.05 significance level. If x bar is greater than u sub 0 plus 1.96 standard errors. Sigma over square root of n. Or if we're also interested in low values being unusual, right, then u sub 0 minus 1.96. So if we know, this is assuming we know sigma, we know that, and we can use the normal. We get this. These two areas here define the rejection region, which is just the region of x bar, the values of x bar, so that we would reject null hypothesis, that they're far enough away from u sub 0. So let's look at one example related to this. Right, so does the human body, what's the average human body temperature? 98.6. Human body. Stated average, so everybody learns, is 98.6 degrees Fahrenheit. And let's say you measured 50 adults, otherwise healthy adults. People with fevers or something, right? You probably would not. So that would be that, or with hypothermia or something. And let's say that the standard deviation of measurements is 0.675 degrees Fahrenheit. Your temperature by temperature is not constant all the time, depending on activity and biological processes going on. It could be a little bit different. The measuring instrument, has to be put on their tongue in a certain way, so it interacts both with you and the ambient temperature, so it's not perfect, right? So there's a little bit of variability in measurement that happens. And let's say that X bar in these 50 individuals is 98.26 degrees Fahrenheit. Is this consistent with the general notion that it's 98.6? Another way of saying that is this result significantly different from 98.6? Is it consistent with it? Is it significantly different from it? Is this result significantly different? So we're going to set up a hypothesis. Right? We want a null hypothesis to be no difference, no change, standard situation. Right? So what's our null hypothesis? Yeah.
98.6.
Yeah. So the average human body temperature, right, would be 98.6 degrees Fahrenheit. You can either use that symbol or you can write the average in words as 98.6. An alternative, then just saying that it's different for some reason in this sample or this population. Right? U is not equal to 98.6. And we've observed 98.26. Are we going to? What's our conclusion going to be? Is this one too far away from that? I mean, it looks pretty close, right? But is it significantly different? So our procedure would say to take, reject the null hypothesis. Right. If our z value that we would get is less than negative 1.96, or a z value is greater than 1.96 once we standardize everything, this turns into x bar minus. No, if z is less than the u sub 0, the null value, minus 1.96 sigma over square root of n x bar is less than that, or x bar is greater than u sub 0 plus 1.96 sigma over square root of n. And so this lower point, 98.6, is here, minus 1.96. And we said the standard deviation of the measurements 0.765, and we had 50 individuals. Here, same deal over here. 98.6 is the null, 1.96, and this is 0.765 over the square root of 50. This value ends up being 98.34. 98.34 degrees Fahrenheit. And that value, when I calculated it, is 98.81. Right, so if our x bar is less than 98.34 or it's greater than 90.81, it's going to look a little bit unusual. Now I said that our x bar out of these 50 was 98.26. So it's just a little bit less, right, than that lower limit. So just a little less than the lower limit, which was 98.34 degrees Fahrenheit. So the conclusion is to reject H0, average temperature is a bit less, right, than the 98.6 based on this sample. And so the logical hypothesis testing would say that 98.6 might have been a number that came from some reference population, but some people taking healthy adults, and it seems that the average is a little bit less. The biological difference is 98.6, kind of more of a fiction that was established in some time. Maybe there's some difference with these individuals. It's an unusual sample, like kind of a freaky result, right? But it is statistically significant in the sense that it's less than that cutoff, right? In terms of our picture, we are getting something, this is I'll draw a new picture for this situation. Here's 98.6, here's the null hypothesis. And then we get two cutoff values here, 98.34 and 98.1, I think. And we got actually 98.2 or so. We got 98.26. So although it's not too great in magnitude, based on the sampling distribution, it's a little bit less than that 5%. Because it's out in this freedom, we do in fact reject the null hypothesis. But in most cases, we don't actually know sigma. We usually don't know, and we usually estimate it from the data. So maybe this is using a different measuring instrument, like a better thermometer to put under your, on your skin rather than under your tongue, or something like that, right? And so, the variation on this theme. So variation on this method. Same logic, same essential characteristics, just one little twist is that we have 50 individuals. We have an X bar of 98.26 degrees Fahrenheit. And now the sample standard deviation is at 0.765. So instead of being kind of a known population value that you're taking on faith, this is estimated based on our data. So instead of, so say still this alpha significance level 0.05. We're not going to look at a normal distribution anymore when we're dealing with means. We're going to look at a t distribution, or n minus 1 degrees of freedom, or 49 degrees of freedom. In this case, here. Right, so t is just a little bit wider. Right? Because by estimating S instead of giving a known sigma, there's a little bit more uncertainty, a little bit more variability in the whole process. Right? We're still going to find the cutoff point that has 95% in the middle, 2.5% on the sides. Right? And with this t distribution, it's actually 2.01. A little bit, this QT function in R will give us the percentiles or quantiles for a t distribution. You can put in the percentile you want in degrees of freedom, so about 0.201. The 49 is not in our t table, right, because it jumps from like 30 to 60, things like that. But that's kind of at the midpoint between two two places. So our table would tell us, something like 2.01, 1.99. So that's kind of in the middle. 2.01 is pretty close. So 2.01, negative 2.01. So we're going to replace, we're going to reject the null hypothesis. If our x bar is greater than the mu sub 0 plus a t-value times s over the square root of n. And so it's then 98.6 plus our t-value 2.01. A little bit more is required. And the s 0.765 over the square root of 50. And that cut off. We'll get that number shortly. If it's greater than that, or if x bar is less than mu sub 0 minus that same t-value, 98.6 minus the 2.01 times 0.765 over the square root of 6. So 98.82, or 98.38, 98.39. This one should be 98.39. So just a little tweak on there. There's not much difference. The sample size of 50 is pretty good. 2.01, 2.0 versus 1.96. Not that much of a big difference, right? But it is the correction that makes it work. So 9.98.8. And then the top one, 98.82. And again, our x bar is a little bit out from that, so we would reject the null hypothesis. It does look different for whatever reason. Is it biological that there's a difference, or is it some bias of our measuring device? That's a different question. That's harder to get at. But there seems to be a slight difference. Maybe that's not so important in terms of really determining health and measuring things, but there is this little difference. Any questions about it? So one way of doing this test, there's really three ways of doing the test. Right? One way is to calculate what you reject. Three ways to test it. In all the ways, you're going to do the same thing. You're going to set up a null hypothesis. You're going to set up an alternate. If sigma is known, we're going to use normal. If S is used in place of that, we're going to use a T, within -1 degree of freedom. There's really three ways to test. Is find, first what we've got is find the rejection region. For an alpha level test. Right. The second way is to find a test statistic. Convert it to a Z or a T, and then do the comparison on that level. Find the test statistic. Which is either going to be a T value, a Z value, or a T value. We'll do that in the next one. Or compute what's called a P value. And they're all three going to be equivalent. You're going to get the same conclusion no matter which way you do it, but sometimes people look at it one way or the other. They're all connected because one's just related to the other. Compute a p-value, which is, anyway, we'll do that, right? We reject H0 for small p-values. So just one kind of side, what is alpha? What is this alpha thing, this significance level? So it's like 5%, 1%, or something like that, right? So alpha is going to be what's called the probability of a type 1 error. That's what it's called in the hypothesis testing world. It's the probability you reject the null hypothesis if H0 is true, really is true. It's a certain type of error. We don't want to make this error very much. And so that's usually controlled at 5% or 1% or something like that. It's set pretty low, kind of by standard. Most journals use 5%, and most results would do that too. Right? So when we're looking at distributions like T or Z, you know, we have the, or if it's on the scale of X bar, right, then we use a 0, it's going to be in the middle here, equivalently. Right? And we're going to reject if we're very far away. We're going to reject the null hypothesis if X bar is large, or if this is like a T statistic, once we standardize things, if the statistic is large. Right, it's a one-to-one relationship here. And then alpha, we're going to have kind of 1 minus alpha as the area in here, like 0.95, if alpha is 0.05. And the areas where we reject is these extra areas out here. So this area is actually alpha over 2, and this one's alpha over 2. So at a 5% significance level means we make the wrong decision 5% of the time when the null hypothesis is true. Right? You don't want to throw out the status quo, standard, no change, when it's really, that really is the case. And we don't want to make that mistake more than 5%, so we set that standard. So let's look at a new, different example. So there's about 7,700 lakes in Florida. And let's say you're taking a sample of 53. And of interest to us, it's a measure of alkalinity. And its value of interest is 35 milligrams per liter, the measure of alkalinity. I don't know the chemical science to tell you a lot more about that, but say that's of interest. We don't want to be too high above that. In our sample, we get 37.5 milligrams per liter, and the standard deviation of these is 38.20. Is that right? That's what it says. So it's pretty skewed, actually. You know, if it has to be positive, greater than 0, if you have an average of 37 and a standard deviation that much, it has to be pretty skewed. Some lakes are pretty bad, right? Just like extremely high value of that. And we're interested in are the lakes above 35 on average or not? So we're going to set up this thing of interest at 35. And in this case, we're going to ask, are the lakes on average more alkaline? So some hypotheses are phrased as one way or the other. Right? And in this case, the concern, I guess, is that it's greater than 35. Now we've provided a sample values. We don't know the alkalinity standard deviation for all 7,700 lakes, so we're not going to pretend that sigma. We're going to use a t distribution. Degrees of freedom n minus 1 is 52. And we are, if we want to get the rejection region, at what values of x bar do we reject? What values us to reject H0. For this type of one-sided hypothesis, we're just going to look in one direction. So we're going to put all the 5% on one side. Many of our problems, like on exams, if you do things two-sided and put half and half, that'll be fine. If you write the hypothesis as one-sided and put everything on one side, that'll be fine. You know, we're not going to get into that too much, but it comes up in practice and really interpreting things. But it's a technical detail that we'll be kind of understanding about it. So if here is mu sub 0, the alternative says that it's bigger, lakes are more alkaline. So we're going to put all 5% up here and the 95% below. So we're actually going to be interested in this 95th percentile. And we want to see, are we actually above that? Right? If it's above that, that seems unusual in the direction of the alternative. So under T, right, with n minus 1 degrees of freedom, here is 0. This cutoff value of 0.95 and 5%. I don't think I have that looked up, so let's get it out of the computer. So I'm going to pop that there and make this smaller. I can kind of get them both on there. We can get the 95th percentile for a T. And now how many degrees of freedom? 52, 53 minus 1. Right? 1.67, 1.675. Right? That's the T value. I can actually write 1.675. That's the T with 52 degrees of freedom. So we're going to, what values of x bar? We're going to reject if x bar is more than 1.675, standard error is bigger. So we reject the null hypothesis that it is 53 if x bar is greater than 53 plus 1.675 times standard error. 37.5. Did I put 53? 35. 35 is the value of 53 is the sample size. And we use 38.2 and 53 is 38.2. And the square root of 53 there. So we're going to reject if x bar is greater than that. What is that? So if x bar is greater than 35 plus 1.675 times 38.2 divided by the square root of 53. If it's greater than 43.7, we will reject. Reject. What do we say we actually got? In this case, we actually got, in this case, 37.5. So it's greater than 35, but it's not so far out there. Right? So we do not reject. Because x bar is only 37.5 in this setting. So it's not so far out there. It's bigger than 35, but not far enough for it to conclude that the statewide average it can't be 35. It might not be 35, it might be a little bit higher, but based on our sample, we can't really throw it out and say the whole state is higher. So that's the kind of x bar rejection area method. The test statistic method calculates a t-value at x bar minus mu sub 0 divided by s over the square root of n. We calculate how many standard units away from mu sub 0 we are. Right? So s over the square root of n we've used before. Right? But we put in our actual bar 37.5 minus 35. And we divide that by the square root of 53. And it was S is 38.2. Okay. 38.2. And we get a t-value, a t-statistic. This becomes some function from our data, because once we have our null value specified in our data, we get that number. And, right, I do have that one. 0.476. 0.476, about half a standard error. Right? Half a standard error is not too extreme. Well, you kind of get out past 2. Right? So it's going to be kind of in the middle of the distribution. So if you compare that to a K distribution with 52 degrees of freedom, n minus 1, 53 minus 1 is 52. It's pretty much near 0. And this test statistic method has given us a value at 0.476. And so it's not out there in the extreme tails at all. What would be the t-value that would surprise us? Well, the thing that cut off that back over here, the t-value that cuts off that upper tail is 1.675. So we'd have to get that far above to really be surprised. So do not reject because our t statistic is less extreme than the 1.675, and that 1.675 came from T distribution with 52 degrees of freedom, 1.675. Do not reject because T statistic is that, it's less extreme than that, right? So mu sub 0, 35 milligrams per liter might be the state average. If we had done something to kind of clean up the water, and we'd hope that it would be like this. If in pollution, we had measurements of pollution were increasing or something like that, and we just use it 35. We can't reject 35, even though it kind of looks, it's a little bit higher, but it's not significantly different. We couldn't rule it out. But any questions over this? If you had, sigma is known in this case, then we would calculate instead of a t-value, we would have calculated the z-value. Like sigma over the square root of n. And then we compare that to areas for a normal. One-sided or two-sided. The other way that this gets done, right, is this is with p-values. Right, so p-values are going to calculate the probability we get something as extreme as we got before, but more extreme. We'll just do one of these examples. p-value method. P-value is the probability that we get a result as extreme or more extreme, as extreme or more than our actual result. Assuming H0 is true. Okay. So kind of a mouthful. So assuming the null hypothesis is true, and we've seen our x bar, what's the chance we're at that x bar or more? As extreme as we got or more extreme. And that's quantified as called as its tail area, looking in one direction. And we convert that to a p-value. Right? So if the null hypothesis, so let's just do it, begin this way, that your sampling distribution of x bar, and here's the null hypothesis. And we're going to observe x bar. We're going to observe that value there in our sample. Now, assuming the null hypothesis is true, this is the sampling distribution of x bar at the null, right, centered at the null. That's how we ask what's the probability we get something that we saw or more extreme, right, when this is true. That is, we calculate a probability under that area, under that distribution. So normal, centered at u sub 0, variance sigma over square root of n, or a t, where the scaling factor is s over the square root of n. This little area here is called the tail area probability. And if our alternative hypothesis is one-sided, that is greater than that, then our p-value is equivalent to that tail area. And we reject the null hypothesis if the p-value is small. Generally, if it's less than something like 5%, right? An alpha level of 5%. If it's smaller than that, if it's more rare, and we're out in the 5% tail or further, right, we're going to reject. If the alternative is two-sided, and we'd be equally surprised by things that are big away from the middle or small away from the middle, we double that. We double the tail area. We call that the p-value. Right? If the null hypothesis is the same and the alternative is just that it's not equal to that, then our p-value that we'll compute is 2 times the tail area probability. Accounting for the idea that we'd be equally surprised if null hypothesis is really true, if we got really big or really small, right? Either way, it's equally surprising. So again, if p-value, right, is less than alpha, like 0.05, then how do you get a small p-value? You get a small tail area. That means x bar has to be farther away. X bar far away, big t statistic, because x bar minus mu sub 0 is big, or p-value, really small. They all tell you the same conclusion, but you can phrase it in terms of, it's commonly phrased in terms of these 3 ways. X bar is something that causes you to reject. Is your test statistic, your t or z, extreme, or is your p-value small? It's all the same thing, but just different ways of looking at it. Let's look at one example. So, not so much a biology example, but let's say you're looking at the braking distance of cars that are traveling 40 miles per hour. And say current brakes stop and an average about 120 feet. And let's say that the standard deviation is 10 given to you. And you test 36 cars, and the average braking distance is 117.2 feet. Probably professional drivers, really sophisticated equipment, closed track, things like that, try to stop. Maybe these are based on new technology, right? Maybe there's a different situation though. Maybe if you substituted a part from another manufacturer that does things with plastic instead of steel, or cheaper aluminum, or maybe you're importing parts of the car from another country, and you might just be interested, is it the same or not? So, is stopping distance. Do you want to do one-sided or two-sided? Let's see, is it better? Maybe this is better technology. Two-sided? All right, so we'll do, is stopping different distance any different? That, we're going to set up a null hypothesis and an alternative hypothesis. Right? What value do you want for the null hypothesis?
107.2.
Is that what you want for the null hypothesis?
No, I think 120.
120. We want the hypothesis about population, or know, what was before, what we know. Right. Is it clear that it would be 120 is kind of what you're given coming from the past, right? And these 36, right? This sample gives us that. So that's only 36. It's not universal knowledge or something like that. Industry knowledge. So yeah, so the null hypothesis would be set up as the old 120 feet. And the alternative is just that it's not 120 feet. Now, if sigma is known, we're going to use the z value. And if we use, say, a 5% significance level, two-sided alternative, not equal, then z value is going to be 1.96. Or plus or minus 1.96. Are we going to be concerned with that? When do we reject? U sub 0 minus 1.96, our z value. Sigma over the square root of n, or u sub 0 plus 1.96, sigma over square root of n. If x bar is less than that, or x bar is bigger than that. And so we have 120 minus 1.96, sigma is 10 over the square root of 36. This ends up being 116.73. What did I say we got? We got x bar 117.2. Do we end up rejecting the null hypothesis? It's not quite far enough away from 120 to reject it. Right? Because it's not less than this low. It's certainly not bigger than the upper one. It would be 120. Plus 1.96, and then 10 over the square root of 36. That upper limit, which is not really in play here, is 123.27. Right. So x bar is not in the rejection region. What would be the z statistic associated with this if we had done that? We take x bar minus the null hypothesis over this sigma over the square root of n. So that z value is 117.2 minus 120, and then 10 over the square root of 36 gives negative 1.68. So it's a bit away from 0, but two-sided, we gotta go to 1.96, or negative 1.96. It's not quite far enough away as a z-value. So, conclusion, I write a conclusion up there, right? So this one, 117, do not reject. 117.2 is not less than 1. That cutoff was 116.73. That would be the conclusion, just looking at the X bars and the rejection region. This one, do not reject. Because our z value, negative 1.68, is not less than negative 1.96. Right? And so that would be the conclusion that way. Yes?
So on an exam, you want us to have those statements?
So usually there's a conclusion statement, right? And you only have to do it one way, right? So some conclusion about what you actually decide. You accept the null hypothesis, you reject the null hypothesis, and why.
You only have to do one of those?
Yeah, just do one of those is fine. Right? But the book will show, or you'll see in the literature different ways of expressing it. And the third way, what's the p-value? Tail area. So you have 120 on the X-bar scale, and that's using 0 on the normal scale. We have a similar shape. Negative 1.68 is here, 117.2 is here, and tail area, right, is the probability we're less than this, is the probability we're kind of badging here. Right? So the probability that a standard normal is less than our negative 1.68. This is would be our z statistic that we calculated off the previous. What's the chance we're less than negative 1.68? Let's get it. There's a probability for a normal, p-norm. Is a probability that you're less than a certain value on a normal with negative 1.68 in there. So at 0.046. Right? So the chance you're less than that is a 0.046. But if we're in a two-sided situation, right, where we're just asking, is it 120, and we'd be surprised if it was really small or really big, right, technically our p-value is 2 times that area. So 0.092. So in this case, we do not reject. At a 5% significant level or 5% error rate level, because the p-value is greater than 0.05. So with the p-value, you calculate the p-value and it translates to the same conclusion in every case. Everything matches up, right? Because it's all kind of one of the same. But one focuses on X bar in the rejection region, one focuses on the test statistic, and this one converts it to the tail area p-value. What if this was one-sided? What if I came in and said, gee, I have this great technology, we've done preliminary testing, I'm sure it's going to make things better, and we're going to stop sooner. I'm going to do a one-sided test. What would the p-value be for a one-sided test?
0.1?
No, not 0.1.
Wouldn't it be double if it's one-sided? Oh wait, no, it'd be half.
It'll be half, right? If it's one-sided, if you only care about it being less, you're only going to look at that little tail, right? You're going to only look at one side. So it's just going to be the probability that it's less than that it would be 0.046. It would just be a little bit less than 0.05, right? If you really kind of could justify it and say, I've done preliminary testing, I'm sure this is going to be less, let's go test it out on the track, get 36 measurements, it's less, and it's statistically significant. So if you really kind of believed it, you could do this one-sided thing. You know, for communication, it's best to tell me, not just is it significant or not, but what's the p-value? What's x bar? Well, what's mu sub 0? Show me the graph of the data. Right? Do all the things that would be in good communication. Often in articles, there's a temptation to reduce it to the p-value is below or above 0.05. You know, it doesn't tell you as much, right? So, but if you tell me that there's this difference of about 3 feet, well, you know, 3 feet in one traffic stop doesn't seem like much. But if that is magnified over 1 million times, and that stops 1,000 accidents, then that seems like maybe something that is worth doing. Now, if it raises the price of a car by more than $500, to add the new technology, maybe that's another consideration. But so that's essentially the idea of this. The other variation of this, this particular example, we had what was 36, and x bar was 130.2 feet. Instead of knowing sigma, maybe this has been s. What is that value of stopping? 10 feet. This is a number based on the sample, right? So you've changed the technology, or in the other imagined scenario, you've changed where the products are coming from, so it's a little different manufacturer, so it's going to affect things, right, on that. And so in this case, you're going to use the t distribution for everything, n minus 1, t with 35, and under that t distribution with 35, it's two-sided. We're going to want the 0.025 tail up there, and that 0.025 tail is 2.03, not 1.96. Or if we do one-sided, it's also 0.025. So the point of this value is that's a t critical value for two-sided. But when it's one-sided, it's less. It's about 1.69 as a value. In R, did I say that before? There's a quantile t distribution that gives some values. So QT of 0.975 with 35 degrees of freedom is that. And then that with 0.95 area is that value. So you're going to calculate the same test statistics, right? You have to change the values of standard deviation. But instead of comparing it to 1.96, I'm going to compare it to 2.03. It's not going to be significant. One-sided, it's really, really quite close. Right? So the test statistic is negative 0.68, and it's within the third decimal place of either being significant or not. Some people, will make a cut point, insist, if it's below this, you can't. If it's not below 0.05, then it's not significant, and you can't report it. But really, there's information there. Instead, publishing negative results, although you have to convince a little more persuasive, and it can be done, and saying, I tested it, and it didn't end up being significant. That could be very important for medical studies or transportation studies or whatever. If you tried a bunch of things and it didn't make any difference, you don't want people to spend a lot of money to try and test that same thing again. But anyway, telling me that the test statistic is negative 1.68. It's a lot more informative than just telling me it's either significant or not. Because then I can judge how close it is and act whether whether it's, it seems to be borderline in this case, really, so. But anyway, that's the logic. On Friday, we had done simulation, kind of randomization. These are some formulas for it. And there's different ways of looking at it, so it starts to look complex, but just keep in mind the underlying key goal that we're trying to do. And if you keep that back, we'll have to more examples on Wednesday.
That's what the process for.
Thank you. Bye.
So I'll just run up to your office and then
Yeah, we can meet there for just
have a
a
quick discussion. And yeah, I've been looking at, so I looked at the Wikipedia page that you sent me,
Yeah.
and then I went on to datascience.com, and Oracle kind of had a
Oh, yeah, they were
good
doing that too.
article on it. So I actually printed that out because I was taking notes on it, and I realized that it would be better off to have it as a
Sure.
reference overall
As a
for the
reference.
future too. So
We can just walk over there together, just upload this one.
yeah, I think I have a good idea of like what it is, the clustering algorithm and stuff like that. I guess it'll just be more of our conversation, maybe more geared towards how